Welcome to our talk on Android graphics. We gave a talk on the similar subject 2-3 years ago. I don't know.
I
think
don't
we gave it
remember
here. I don't know. So we had this idea that not enough people are doing graphics programming because maybe they haven't actually played with the APIs and realizes that it's a lot more fun than the rest of the stuff.
It could also be because the APIs are not really well documented
So-
or easy to understand.
Yeah, there's a certain responsibility to maybe help explain how things work, but also just some of the fundamental concepts. If you didn't take computer graphics in school, if you haven't sort of focused on that, then maybe it's not obvious how the stuff works. So we thought we would sort of do little introductions to some of the technology. Last time, it was fairly non-Android specific. It was just concepts like what's a bitmap and what's a pixel and how do these things work, colors, stuff like that. Today, we thought we'd focus on a particular aspect of technology, of graphics technology, as well as how that stuff works in Android. So this, in fact, is part 2, which we can also call the path to enlightenment. There's a tiny wordplay in there. I don't know if you catch that yet or not. It's hugely clever. I'm Chet Haase. I'm on the Android graphics team. Surprise, surprise.
And I'm Romain. I used to be on the graphics team, and I'm on the toolkit team now.
And I used to be on the toolkit team, and now I'm on the
And I used to be on the toolkit team also before.
Yeah, it's just the same thing over and over and over
And then
again.
we did graphics and toolkit before Google.
Okay, so all of this stuff is basically about vector-related technology. So first of all, it seemed useful to explain what we mean by vectors. So we can compare most of the rendering technology that you see on Android and everywhere else kind of boils down to 2 basic approaches. There are vectors and there are images. Images are generally used for supporting, what's that called? An image. Right, so photographs, these pictures of information up there, versus vectors, which are really good at supporting things with lines in them, strokes and fills, more geometric, you can think of it. You can also think of the difference between these as the same difference between if you use design tools, Photoshop and Illustrator. So Photoshop works with images, works with bitmaps, works with pixel-specific information. Illustrator works with vectors, right? So that's why you go to Illustrator to draw lines on the screen, you go to Photoshop to import and filter your photo. And they don't really mesh entirely well, but this is why, sometimes you're working on one tool and you'll end up with this, jaggies in the result because it wasn't working with vector information. Anyway, so there are advantages to either one. Let me talk about some of those. So with images, they're really important for representing specific pixel information that you want. This is the photograph that I wanted to represent. I didn't want to dumb it down and have some approximation of that information. I actually want to see these specific colors in those specific pixel values, whereas vectors, and yes, so preserves fine detail, also really fast to render, right? Like the GPUs, the CPUs, the hardware that we're dealing with both on desktops as well as mobile is really good at copying images around. That's basically what GPUs do. They draw triangles and they copy images around. So once you have the thing loaded into memory, the operation of actually moving that memory from here to there or saying, copy this image, draw this image over there, super fast. So that's a really optimal way of doing that kind of operation. On the other hand, you have vectors, which are really good at representing this geometric information, right? At a very fine level of detail, there are no jaggies there. You can zoom into any level of detail and it will always draw with that fine level of detail on all of the lines and the fills. And some of the reasons why you might use that kind of approach instead is basically infinitely scalable. You can scale this thing up and up and up, keep zooming in, and it will always be crisp in detail because it's not drawing at some resolution and then zooming into that resolution. Instead, it is drawing at whatever native resolution you happen to be zoomed into at that time. It is performing a graphics geometry operation to render that thing instead of zooming up an image, which would be the way that you'd zoom into a photograph like that. It's also really compact. So if you think of images, these can be really large. You take it with a DSLR, that image is going to be very large to download from the network, to load into memory, and to keep resident in your application memory. Whereas vectors are basically drawing operations, incredibly compact to say, move here, draw there. Size ends up mattering, so these images, as I said, can be huge, both in terms of the size the image is stored in, but also strangely confusing to some people, the size of the memory that it takes up in the application. We've had, on multiple occasions, People asking us, hey, I have this really tiny JPEG, but why did I run out of room in my application when I loaded it as a bitmap? I'm like, because it's not the same thing, right? Like you can represent JPEG in a really compressed format, but when you load it in as a bitmap, that size is going to be width times height times 4, essentially, right? No matter what size the JPEG was, doesn't matter. It's going to load in at the size that the bitmap needs to be. Meanwhile, vectors, as I said, are really compact. It's just the drawing operations themselves. You're not going to get that fine level of detail that you do in a photograph, but you're going to get that infinitely scalable resolution with really small footprint, both in terms of download size, if you're downloading assets, or the runtime size, that operation that is resident in memory in your application. Scaling also matters. I mentioned this already. So if you scale in an image, like let's say the native resolution of that image is similar to what we see there for the little rounded rectangle thing, and if you scale it up, you're going to get artifacts. So if you look at the corners, you get that aliasing there because it simply didn't have any more information to work from. You want to keep zooming in there while all it's got was the original pixels in that original image. Whereas the vector representation on the right, no matter how far in you scale, you are still going to get a smooth representation. This is dumbed down a little bit for Keynote. I should point out, like, if we were actually zooming in on a vector operation in Android, you would have the same stroke width the entire time, right? So here the stroke is being zoomed, so not totally realistic, but you get the point. Look at the corners there. That's what you would get on Android because it's just drawing a round rect at whatever resolution you happen to be at. All right, so you can represent not just the lines that we're talking about here, but also shapes. So you have these different shapes that you can represent over here, as well as tons of other ones. We'll see some more as we walk along here. How it boils down in Android is basically operations in Canvas. So you can draw a line, you can draw a rectangle, you can draw a round rect, you can draw a circle, and you can draw whatever this thing is here. It looks like the protractors that we used in grade school. So you can draw that path. And you can fill that path, you can stroke the path. The stroke is the line around it, the fill is the fill in the middle of it. And the question is, what is that path operation? So we're going to look a little bit about, into a little bit about how paths work, basically for the rest of the talk. So path, you can think of as a geometry or a drawing container for all kinds of vector primitives, including lines and circles and rectangles, more operations. You can connect these things together so you can draw a line and then you can draw another line and you can draw a curve and you can add a rectangle, and this can all be part of the same contiguous or even discontiguous path there. And importantly, you can also represent Bezier curves here.
Yeah, so Chet's going to explain a bit more what Bezier curves are, but what's interesting is, for instance, circles don't exist on Android. Under the hood, what happens that the circle is turned into a bunch of those Bezier curves on your behalf. Same thing with the rounded rects. So those are just facilities because they're easy to use, but under the hood, it all boils down to Bezier curves and lines.
Yeah, so it's interesting. Like, we could basically base our entire drawing operations, all of the stuff that you could do in Android, on curves, except we probably buy a little bit of performance by being able to just draw a straight line. But otherwise, things kind of boil down into Bezier curves anyway. So our API could be simplified. If we just took away like 90% of what's in Canvas, it'd be a lot less confusing. Just curves. Everything's curves all the way down. All right, so what are Bezier curves? It is a parametric curve between essentially two anchor points that anchor where that thing is going from and to, and an arbitrary number of control points between them, which essentially control the curvature or the slope that the curve takes in between those two anchor points. So here's a graphical representation because it's a graphical talk. So here's this simple curve. This could be represented as a cubic Bezier. You have the anchor points on the end, and then you have these two control points in the middle. And the control points you can think of as controlling the slope as it leaves one anchor point and then goes toward the next control point and then into the final anchor. So this control point, for example, controls the slope that it's going to have as it leaves that anchor point. And this is important to realize if you use any design tools. We'll see a screenshot here in a minute. That's essentially the information that it's trying to communicate to you is what is the slope that this curve is going to take at that anchor point. And the the way that you drag the control point determines what happens to that slope in the curve between the two anchors. So you can represent this with a complicated looking function, n choose I over, the rest of that stuff. As t, the parametric equation variable takes values between 0 and 1. So basically, as it goes from here to there, it's following this function there, this equation, and taking on those values. That's a little confusing to think about. One of the things to realize, so I'm talking about Béziers in a very generic way because you could really have any number of control points in between the two. Realistically, we don't really deal with much beyond cubics, and in fact, you could represent everything with cubics. So we'll see how to simplify that. If you look at a linear representation, that's simply a linear parametric equation here. You basically say, well, given the value of t, you have values for the anchors at either side. You don't have any controls. There is no slope. It's just the line going from one point to another. That's a very simplified version of the curves that we're talking about. One step up from that is quadratic, which I find really confusing because I think of quad as meaning 4, but in fact it only has 3 points. And so math people are obviously not word people.
Yeah, we've been doing this for 20 years and we still get confused by the name. So if you are confused, don't worry, it's perfectly normal.
Because there is a standard form of the Bézier which does have 5 points, 3 in the middle, and that's called a quartic. And neither of them actually have 4. What has 4 is the actual cubic curve. So the word that means 3 gives you 4 points. Again, words, not numbers. Okay, so quadratic, you have one control point in the middle. That controls the slope for both of the anchor points. And the cubic is the one that gets really interesting because then that controls the slope on both sides. And you can get much more interesting curves, even curves that can self-intersect along the way. And you can actually represent all of this stuff with cubics. So a simplifying assumption you can make is no matter what you give me, I'm going to boil it down into a cubic. And that could allow you, so there's some past stuff that I'll show a little bit later that I'm playing around with. And sometimes it's easier to deal with structures that are exactly the same no matter what the inputs were. So if somebody gives me inputs anywhere from linear up to cubic, I can represent that all as cubics, and it allows some simplifying assumptions later on. And on, but we're not going to talk about higher order curves. So if you've used design tools, you may have seen a UI something like this. I forget which one. This may be from Acorn, but there's something very similar in Illustrator and whatever. There's usually some representation of Bézier curves there, and you'll see something like this. So here we see the anchor points, which are represented by squares, in a longer curve. So this is actually chained Béziers where there's an initial curve and then there's another curve joined to it. The anchors here are the squares and the controls are the circles. And you can see directly in the UI of the design program that it's telling you this is what the slope is going to be at this point. So you can see it's a straight line, straight shot up to that control point. And same thing over there, from that anchor point, straight shot down to that other control point. And then typically in these design tools, you could have a discontinuous slope there. You could go off in a completely different direction starting at that second anchor point. But usually design tools do what you want them to, which is to match slopes when they chain curves together. So in this case, that position of that overall line between the two circles is going to determine a slope both coming this direction and the other direction from that anchor point, which then gives you a slope that matches for both of those chained curves. All right, so now let's talk about Androids. So the way that you get this technology from Android is you create this path object. And then you tell the system, okay, pick up your pen and put it down here. I want this to be my starting point for the curve. That becomes your first anchor. And then every operation from that basically builds on the previous point. So you say, I want a cubic from that point that I gave you before, and here are 2 control points and another anchor point. And that takes you to the next point, and then we chain on another one from there, give it another couple of control points, which assumes the anchor that was established on the previous operation, and then we draw the path, and we're done. All right, so this one was, let me show you how this works a little bit in practice, if I can manipulate this. All right, so, wait, was this the one? Yeah, that's the one. Okay, I have 2 demos, one's a video, one's a demo. All right, so here's a little Oh, this is going to be hard to do. A little Compose app. This is my first Compose app. Aren't you proud of me?
So beautiful, Chet.
Isn't it?
No, it's terrible.
Lie. Okay, so here is some code I wrote that draws a path given a certain number of control and anchor points. Right now, I just have 2 points existing, so they both function as anchor points on a linear curve. Let me add a point to them, so I will select this, I'll select that. We'll add a point in the middle. This becomes a control point in the middle, and you can adjust the curve. I think most of you have sort of seen better versions of this in professional design tools instead of my first Compose app. We're going to add another point, and that becomes another control point. So now we have a cubic Bezier instead of a quadratic. And then if I add one other point here, then it becomes an anchor point for the next curve. So it basically only handles up to cubic functionality because I didn't really want to deal with higher level curves. Also, the Canvas API basically takes you up to a cubic, and then after that you need to chain. We don't do higher level curves. You'd have to be on your own for doing that. And you can see there's a discontinuity in the slope here because nothing about this control point has anything to do with the next chain in the curve, so there's a little break there. Probably not what you want in your final result, but it at least shows you the basics of using it. We're not going to talk about this stuff, but there's also some stuff in here to control. You can do things like control the width of the stroke, and let's see, you can do mitering, which changes the way that the chains curves relate to each other as they round the corners, and you have different rounds, all of those things. But the interesting thing is the code. So here's this canvas that I have in my first Compose app. As I drag around here, I double tap will add a point, or tapping selects a point, and then you can drag things around. You can click on the button, which adds a point, which I was doing over there. And then this is the rendering code. And all of the canvas drawing that's showing that stuff there is not that. That's not what I meant. Is basically this draw path command. Passes in the parameters to draw with. And then the circles are drawn. That's kind of a debug thing. So you can remove those, and it doesn't draw those, or optionally see what the control and anchor points are. And all of that is basically just doing draw circles with different colors and parameters. So the interesting parts there are basically as I create points or change the points, drag them around, then we call this construct path. And that does a rewind. So it takes this one path instance that it has, it rewinds it, which is a base. It's a way to reset it and reconstruct that path. And then we're going to move to the start point again, and then iterate through that and add path segments, which is called up here. And path segments says basically for every one of those paths along the chain, how many points do I have left? And that determines whether, well, I'm always creating a cubic too. As I said before, you can represent linear, quadratic, and cubic all with cubics. So basically, based on how many points I have left, I'm creating a cubic that basically just inserts dummy points in the middle with existing control or anchor points that I have. And that's it. So that's the basic functionality. And now we'll figure out how to get back to the slides. Awesome.
All right, so now we're going to build something utterly useless, but hopefully you will be inspired by the kind of really cool things you can do in the UI of your application by learning about a few APIs that you may have never encountered before or dare to use. So we're going to start by building a path. So I'm using here the Compose APIs. They're slightly different from the standard Android APIs, but the names are a bit different, but everything works the same. So we're just building a path. So here it's kind of like this wavy path. Don't worry too much about the details, the values, that's everything that Chet explained. And then if we were to draw that path, we get what we have on the left. So by default, Android will fill a path and will look like that. This is not what I wanted. So instead, you can change the style of the path to stroke it. And now we have our sine wave. But then I want to do something a little more interesting. So let's say that we want to add a circle, and we want to position that circle on that wave, and we want to be able to move it around. So that's very easy, right? We call the draw circle function, and we need to give it a position. The question is, how do you find the position of the circle so that it sticks to this wave. So there's an API for that, and it's called path measure, which is actually pretty confusing because you're not really measuring the path. But anyway, so you construct a path measure instance. You give it the path object. And then the first thing you will probably want to do is ask for the length of the path. So this will be, imagine if you were to flatten the path, that's the total length of the path in path units, using whatever coordinates that you selected. So they will tell you how far along you can move on that path object. And then you can call this beautifully named getPos_tan function, which really means get position and tangent. And you give it a progress along the path, so it has to be a value between 0 and the total length of the path. So in this case, you don't see it on screen, but I had a slider that changes the progress value. And using that slider, I can just go from 0 to the total length of the path to be able to get the position on the path. And that position is given to you as an array of 2 floats, x and y. We also pass an array to get the tangent. We're going to look at the tangent in a little bit. Actually, on the next slide. So the tangent is given to you as a unit vector. So it's really the direction of the slope at that specific position on the path. You're probably not going to use that function very often. So if we were to just draw a line using the tangent information, that's what we have. Usually what you want to know is the rotation at that point, right? Like to be able to align with the path. Using the unit vector, you could figure out the rotation if you do like an arc cosine of the dot product and all that stuff. You probably don't want to deal with that. So we're going to see another API that's a little easier to use. Another interesting we can do with the path is get a segment. So that allows us to basically trim the path and get only a segment of that path. So that lets you build this kind of animations where you can trace the path. So here I always trace the path from 0 to whatever is the current position that I want. But you don't have to start at 0. You can take any trimmed section of that path. So to do that, you call getSegment on the path measure object. You give it a start. Here it's always 0. And again, you give it a final position that has to be between 0 and the length of the path. And as we animate, and that gives you back, so the last parameter after the length is the destination path where you want to store the segment that you're asking for. And then once you have that secondary path, you can draw it as just a regular path, and you're going to get the result. So now we're going to make it a little bit more interesting. We're going to use one of the default material design icons, this beautiful sailing boat. It's a vector painter object. And we're going to try to draw it on our path. So this is how you draw it. We're going to give it a position. So that's the position we got from the getPos_tan API. And now we can move our little sailing boat with the waves. It's not working really well because it's not rotated, right? It doesn't align with the ocean. So we're going to see how to fix that. So I mentioned before you can get the tangent, but it's a little cumbersome to use. So instead you can use this getMatrix function that will let you achieve what you see on screen. So if you call getMatrix, once again, you give a position between 0 and length, you give it a destination matrix, and you have to pass flags. So the OR here is the binary OR, so Kotlin does this thing that really pisses me off, where it's not the traditional binary operators. So this just means we want to set both flags. So we want the matrix to contain the transform for the position, and we want the tangent, so the rotation as well. So once we have this matrix with the position and the rotation, then we can just apply the matrix as a transform before we draw our vector painter that we got from the material design icons, and we automatically get the position and the rotation of the icon. All right, so next we can do something even more interesting because our water is a little boring. So we're going to use something called path effects. In Compose, the path effects are part of the draw path call in the style. It's part of the stroke. With the traditional Canvas APIs, you can set that on the paint object, but they're pretty much the same APIs. So with the path effect, we'll be able to do something like this. Instead of drawing the path itself, we can stamp another path along our first path. So here I have an arrow that I built myself. And if you call path effect.stamped path effect, you give it a shape, so that's the arrow we want to stamp along. We're going to ignore the phase. And then you have the advance. The advance is basically the spacing between two instances of your stamp along the path. So here I just pick something that look decent enough. The last parameter is more interesting, so it's the style. So by default here I'm using translation, and you can see that once again the stamp is not aligned with the path itself, like there's no rotation, right? We just put it at different positions, so it doesn't look very good. So if we change the style to rotate, instead we can get this. It's starting to look a little better, but you can see that the rotation, because it's based on the local tangent, it's not completely aligned with our source path. So we're going to use the last style called morph, and that lets us do this. So what it's going to do is going to take your stamp and curve it to match the original path. And so now we have those beautiful waves made of arrows, which is already a more interesting effect.
I should point out something too about graphics programming that we both experience, and I think everybody else does that does graphics, is that when you try to write this stuff, you're like, oh, I think I know how these APIs work, and you'll write something and it'll look completely wrong on the screen. Like things will be rotated about 360 degrees from the way you want, or 180, I guess would be the opposite. And like they're flipped, they're skewed, they're like things are just wrong. But the awesome thing about graphics program is you can see them, right? You don't have to write a unit test to see whether the facts are correct there. Instead, you see, oh my God, that is so wrong. And then you just start dorking with the matrix and you're like, okay, well, where was the translation and where is the, and like, it's a really satisfying debugging experience, I think, where this probably didn't look like this the first time you wrote it.
Speak for yourself, it did look like this. No, it didn't.
But then you look at it, and then you can kind of reason the result. Oh, I see what happened there. And it's just kind of this satisfying, like, aha moment that you get every time you try to make this work.
And so now here comes the phase parameter. So the phase just lets you apply effectively an offset for the stamps. So if we animate that phase using the progress value that we've been using all along, you get this nice animation of the stamps. As you draw the path, you can animate what's inside the path. All right, so now that we have all that stuff, let's pick a different icon. So I pick those waves that come with Material Design. And then if we stamp that along our path, oops, that's, let's start. Come on, video. Yay. So now we have our little sailing boat over the waves. So I don't know if you're going to draw that kind of sailing boat in your application, but using those APIs, you can see that just in a few lines of code, you can do very interesting things, right? It could be a progress bar of some kind, or any other kind of effects that you can imagine. I really invite you to look at the path effects. The stamped one is not the only one. There are other path effects that we provide. I really invite you to look at them and see what you can do with them. And of course, you can do more complicated things. So this is a demo I wrote a few years ago that's using the get segment API. And you can see that what I was doing, I was loading SVG files and I was animating the get segment calls to be able to do this tracing of really complex vectors, so like all the United States of America, and then as you scroll, I was triggering both on text and those states interesting animations. So it's just to give you an idea of what you can build with that. Now we're going to look at something else I've done a few years ago. I wrote a blog about it. It's how to use paths to improve text. So let's say you have a piece of text and you want to underline it, and it's going to look like this. And pardon my French, but it looks like shit because the underline crosses all the descenders, right? Like it crosses through the G, the Q, the Y, and the P, and especially on the G, like it just looks busy. Instead, we can make it look like this, so you can see the difference, right? And we're going to see how to achieve that using our path APIs. So the first useful path API that you can use here on Paint is called getTextPath. It gives you a path that forms the outline of the piece of text that you pass. So you give it, in that case, I give it a path called outline at the end. And if I draw this path as a stroke, I'm getting the result that you see on screen. Then I'm going to build a path that contains only a rectangle for the underline. So we're going to use the getTextBounds API to know how wide the text is. Then we're going to create a path object. We're going to add a rectangle to it. For the width of the rectangle, it's super easy, right? We have the bounds. We go from the beginning, from the left to the right. For the thickness of the underline, starting with API 29 on Paint, you can get both the underline position and the underline thickness. So if you want to match exactly what a regular draw text call would do. So we do this. So now we have two paths. We have the outline of the text. We have an underline, which is just a rectangle. And then the next step is we're going to take the outline of the text and clip away everything that's above the underline. It's going to be important for the next step. So I create another rectangle. It's not very interesting. What's interesting here is that I call this up function. So it's basically a Boolean operation on the path. So I'm going to apply a difference. So I'm going to subtract our clip rectangle from the outline. If you use the core KTX extensions, you can instead use the minus operator. So you just say the outline minus the clip. That gives you the new path that you see here on screen. And that contains only the descenders, so only the areas that we want to clear around. The next step is we want to dilate. We want to make space around those pieces of text, right? We want to cut stuff around it from the underline. So we're going to use a stroke. So you create a paint. You want a fill and stroke. You set a stroke width to whatever is the amount of space that you want around the text. And then you can use another cool API on Paint called getFillPath. So it will give you another path that if you fill that, it will look like your original path when you stroke it. I know it's a bit confusing, but it makes sense. And if you draw that, you get the result that you see here on the left. So now what we can do is we can subtract that dilated path from the underline by just applying our minus operator. And we're done. Now we can just draw our text, draw our path, and you get this beautiful result. Of course, you can combine those APIs in many different ways. So here I use getTextPath to get the outline of text, and I use a stamped path effect to just animate random stamps along that outline.
This is like a banner ad for your product here.
Yeah. This is just, don't do that in your app, but do something like that.
All right, so one of the things that you may end up wanting to do that is not necessarily obvious how to do in Android is querying the path. I'd like to know what the information is in this path. Right now, the APIs are basically a black box. You say move to, line to, quad to, cubic to, whatever. All of that information goes in, and it goes down to the Skia rendering engine, which is the native rendering engine that we have, the underlying canvas, and it doesn't come back out again. There is no way for you to say, oh, what was that? Where was your starting point, and what did you do next? That information does not exist in the API. However, sometimes you need that information. So, for example, we'll show a little bit of path morphing later. If you are given two paths and you want to animate between those two, you kind of need to know what's in each of those paths. You can't just ask Android to do this thing because we don't have a morphing API right now. So instead, you kind of need all of that data to be able to be extracted so that you can then interpolate between it.
So there are two ways you can do this. The first one is you can write nasty reflection code at the native level to ask to poke at the native data structures instead of Skia to figure that out. Thankfully, I've done that for you. So there's a library on GitHub called Pathway. It works all the way back to API 21, mostly because I didn't bother testing before that. But the way it works, it's pretty neat. So you create your path however you want, and then you just have this iterator. So in Kotlin, you're just going to say for segment in path. And for each segment, it's going to give you the type of the segment. So it can be, we're going to set all the types. So just, actually the code is wrong, it's like segment.type, not path.type. And then it's also going to give you the points, so the anchor points and the control points. There are other APIs to avoid allocations and stuff like that, but basically that's how it works. So that's the other API where you can use a more traditional iterator so you can reuse existing allocations. And when you iterate over the segments, so each segment can be one of the following. It can be a move, so that's the path.move that you do. It can be a line. It can be a quadratic, a cubic, or something called a conic. So conics are a little annoying because when you build some types of path, let's say you add a circle to a path, Skia will create conics. But if you look at the path API at the Java level, we don't have conics. We should fix that. So Pathway will helpfully, by default, transform the conics into cubics or quadratics, one of the two for you. It's an approximation, but it's going to be close enough that it's not going to make a massive difference. You can also tell the API, no, please preserve all the data just the way it is. So anyway, if you were to use that library and you see a conic, don't freak out, just read the README.
One of the other interesting things to note here is if you look at the Path API in Canvas, or in the Path class, there are tons of operations in there. You can add circle, you can add rect, you can add line, you can do cubic to, you can do quadratic to, like path operations, all these operations that you can do on the paths to make it more and more complex. But the data that ends up being stored at all the end of this stuff is everything here. That's why the pathway API is fairly simple, because it's just extracting the data from Skia after all of those operations have happened. You draw a line, that's fine, but what we're really storing down there, well, we are storing lines, but for the rest of these things, we're just storing one of these things. We're not storing a circle, instead we convert it to a path, and that's the information that's retained.
And the last two types of segments are closing the path, so it closes the contour. It's basically the equivalent of a line 2 back to the original point. And then there's done, which means there's no more data inside the path.
So that was one approach. You can do this nasty reflection. It's kind of nice that...
By the way, I want to mention that you should read the source code of Pathway, because it does really nasty things with memory aliasing, and it uses goto in a couple places. It's beautiful. I really like it.
Considered
The code is really clean. You should read it.
So that's one approach. You can do the nasty reflection stuff, and it's nice that Pathway exists so that you don't have to do it directly. You can just use Romain's work instead. Another approach is an approach that I took recently. I've been playing around with some path technology, and I needed that information. I was working with morphing, and I needed to know, okay, well, these paths were created, but what were they created with? So the I would say simpler, more obvious approach is just remember stuff as it goes in. So you can basically create a layer of your own that sits on top of path, and instead of calling path directly, they would call your layered API, and you just cache the commands that come in, and then you can remember that. You can allow people to query them, or you can reissue them later, which is what it says there. Okay, so in my example, I have this class called path commands. It's an abstract class that's then implemented by all the things below it, depending on what the kind of command it is. And it just has a simple function inside of it so that later it can be told to issue something to a path. And that's it. So if we look at some of the implementations here, if someone calls move to, then the issue thing basically just calls the given path with a move to command. Then from that, I created this class called queryable path, which you can then query for this information. It stores this list of commands, so every time somebody calls this API, it basically just adds to that list of commands that exists on this path object. It adds to the list, and then it executes that thing. So it is a subclass of path, or it can delegate to path and just issue the command. So you are getting the path operation that you want, but at the same time, there's an intermediate class that's caching that result so that it can be returned later and worked with. One important thing, so we saw earlier in some of the code that I was showing, I think I used rewinds, but there's two ways to basically reuse path information. One of the things to realize about paths is they can get fairly complex. If you think of some of the complicated icons that are created, or the things that come in SVG assets or Lottie assets or animated vector drawable, the paths go on and on and on. If you're then going to mutate these things, wouldn't it be nice if you didn't have to reallocate everything going on under the hood all the time? So there's two ways to do that. One is that you can reuse the path itself by saying reset. All that does is retain the original path object, but then you will reallocate all of the pieces underneath it. The other is by calling rewind, and this is generally what you want to do. It retains all of the native allocations and then just reuses them as appropriate. So as you issue another move to command, another line to, another cubic to, it is reusing these pooled objects.
And while preparing this talk, we figured out that the compose path object only has reset and doesn't have rewind, so we need to file a bug.
Yep, bug. New APIs have bugs. So do old APIs. All right, so let's talk about morphing. This is the real sort of use case, at least in my mind, for why you want to be able to query these things and why there are long existing bugs asking for us to expose the ability to query paths. So I'll just show a little video here that motivates this. So here, I guess I have to click. So we have these, basically a start path and an end path. There are these two arbitrary objects that we want to animate between. Well, in order to do that, we need to understand the structure that was used on the left and the structure that was used on the right, and then be able to interpolate from them, from and to them. So for that, well, I need to know how that triangle was created and how that, whatever that thing is on the right, was created as well. So a very simple view of how that works in the morphing API is you have one of those queryable path objects that I pointed to before. So someone has created the object on the left with a queryable path that has cached all of the operations that went into that rounded triangle. And similarly for that star-shaped thing that was on the right, the queryable path cached all of those. And then we come in here and basically align the data structures and say, well, given what we have at the start, what we have at the ends, then we can create similar structures between them and then easily animate between those structures. Once we know the data, then we can create and align the data so that it makes sense going back and forth between them. And then it's important to point out that the stuff that we're talking about today is all at the API level. These are the commands that you call in the Canvas and Compose APIs and Path APIs in order to access this functionality. It's also very common for people to use actual assets instead. So the stuff that we're talking about is most commonly represented as things like animated vector drawables or Lottie or SVG assets. And when that comes into your application, it looks something more like this. So if you look at the asset for an animated vector drawable, you're probably going to see something in there looking a lot like this. And that is essentially a move operation to a particular XY location, followed by a line operation and cubic operation, whatever. The Z at the end, I think, is a cute way of saying, I'm done now, I went to sleep. And that is it. We were just called on time, so I don't think we have time for questions. Thank you.